Starting with again, we will do a recapitulation about those people that such Joseph Thomson, who discovered in 1897 about electrons. But though it's a fact that electrons were already previously discovered, or rather previously not discovered, I should say, there's Joseph Thomson. So Thomson actually carried out certain experiments, and in 1886, not in 1886 rather, previous to that, 1880s or 1870s, there were indications that atoms are divisible, but no such clear evidences were existing during that time. So Thomson carried out experiments to prove that electrons are existing, and in 1897 he proved that one. So his experiment was, he carried out an experiment using a cathode ray tube. He carried out his experiment. Followed by Thomson, protons were discovered. But the concept of protons, though it was given, rather the acceptance came to the scientific community in the year 1911. But before that, in 1886, before the discovery of electrons, Eugen Goldstein, he also concluded that protons or positively charged particles existed within an atom. And followed by Ernest Rutherford in 1909 discovered protons. Sorry, I said in 1911. So it was so it's a combined effort of Eugen Goldstein and Ernest Rutherford. So after the discovery of the electrons and protons, there were some other parts, rather in the year 1932, a few years later, almost a decade later, and not even 1 decade rather, it's possible to say rather 2 decades later, Sir James Chadwick, he discovered that another particles existed within an atom, and those particles are neutral, and hence it's called the neutrons. So, and for the discovery of the neutrons, Sir James Chadwick was awarded the Nobel Prize in the year 1932. Sorry, not 1935, sorry. So he was awarded the Nobel Prize for the discovery of neutrons. So now, focusing on the experiments which normally brought out or revealed that there are particles existing within an atom, and the atoms are divisible, and which helped to prove the Dalton's postulates to be incorrect. So we will begin with Joseph John Thomson's, Joseph John Thomson, J.J. Thomson's experiment, the cathode ray experiment. So we'll start our today's, once again, our fresh lectures with the cathode ray experiments. And over here where I'm having the cathode ray experimental setup, as was done by J.J. Thomson. So this is the experimental setup of Sir Thomson. So there is you can see there is a tube. It's called the discharge tube. It's mentioned over there. So it's a discharge tube, and within the discharge tube, there is a very low pressure is maintained inside. So inside the discharge tube, there is a very low pressure which is maintained, and it's the discharge tube is having two electrodes. One is called the cathode, another end is having the anode. Now, cathode and anode, we already know there are two connections of a particular, of an electrical source, an electrical charge source. So the anode is basically positive, and cathode is basically negative. So it is, though we are saying right now it's positive and it's at the positive and the negative end. During that time, it's basically one end rather having a particular source of battery or a high voltage generator. It's particularly having 2 points, and there was a conception that if we connect the 2 points, then there is an electrical setup or electrical energy flows. Now, This particular plus and minus is basically to represent that both the two terminals or both the two ends are not the same. They're opposite to each other. So they're opposite to each other. So one is called cathode, which is another one is called the anode. So generally right now we indicate as a cathode, and the cathode is connected to the negative terminal, and anode is connected to the positive terminal. Now, this setup is basically before the discharge is taking place. Now, before the discharge is taking place, or rather when the discharge is taking place, it's going as we can see, the discharge is there is a discharge of, or radiations are moving across from one particular electrode to another particular electrode. So this is experimental setup. It's without electrical field. So the entire discharge tube is not exposed to any sort of electrical field. That means there is no such impact of the electrical force. So though the tube is there, but no such external effects. Effects means effects in terms of electricity, or rather electrical effects, or no such magnetic effects are there, or from the external, as acting as an external source to these particular these particular experimental arrangements. Now this is basically, as you can see, it's mentioned that this is cathode ray tube, and the discharge tube is exposed in the place where there is no electrical field effect. But later on, after certain moments, it is being exposed to the exposed to electrical fields. So now when it is exposed to electrical fields, Thompson noticed that the rays are getting deflected. It is not reaching the anode anymore. So there is there was a measurement. So it's not shown over here. There was an current measuring unit, or rather an instrument was there. So what happened? He noticed there was a drop in the amount of the current, in an amount of the current received at the anode end, and because the instrument, the recorder, was recording less amount of current compared to the previous one, and this happened when, and this only happened then when the electrical field is being imposed upon the cathode ray tube. So then he noticed that the cathode rays were deflecting. The cathode rays were deflecting towards the positive terminal, the cathode of the electrical field, and that rather this observation made rather Thompson to think that this is a very this discovery is a very significant observation. Just not discovery, rather an observation with respect to cathode rays being deflected towards the positive terminal of the battery. So now these observations forced Thompson to conclude certain things. What are the things? What things to conclude? To conclude the properties of the cathode rays. And he concluded that cathode rays travel in straight line from cathode to anode. This is a general one. Cathode rays travel in straight line from cathode to anode. Now this condition is basically, this statement is with respect to cathode rays when they're not being exposed to any sort of electrical fields. So cathode rays travel in a straight line from cathode to anode. They cause greenish yellow fluorescence on soda glass screen. soda glass screen. So this is once again when they're not being exposed to the cathode. They're not being exposed to the electrical fields. But they cause greenish yellow fluorescence on the soda glass screen. The third we are having, they show deflection in presence of electric field. That is, move towards the positive plate and away from the negative plate. So they show deflection in presence of electric field as if they're moving towards. So cathode rays got deflected towards the positive plate and away from the negative. So they are being deviated from the negative plate, or as we are saying, in presence of the electric field. So electric fields are also having some rather polarity. That means one section is positive, another section is negative. So they show deflection and presence of electric field move towards the positive plate and away from the negative plate. The next, they penetrate through matter. They penetrate through matter. So cathode rays are having penetrating power. So normally the cathode rays do not, they are traveling in a straight line, but whatever they're in, rather lies in front of the cathode rays, they're having the power to penetrate those things. But the condition is whatever is coming in, rather in between, or rather in between the path of travel of the cathode rays, those substances has to be thinner. So there is a certain level of penetrativity up to which the cathode rays can penetrate. After that, cathode rays cannot penetrate any further. Okay. The next we are having, they produce shallow shadow of the object placed in between the path of its movement. So they produce shadow of the object placed in between the path of its movement. So this reflects, that means cathode rays do have penetrating power. So as I said earlier, that they can penetrate after a certain level. After that, if the substance is thicker, the cathode rays will not be able to penetrate. And followed by this, cathode rays also reflect. So that, if that is the point, then cathode rays, they are producing shadow of the object placed in between the path of its movement. This reflects, number one, that it can penetrate up to a certain depth. The second thing it's reflecting that cathode rays, they are having, once again, the apart from these rays are having, behaving as particles, as if that means solid substances. So they cannot penetrate, and hence they are imparting shadows. So thus, since it cannot penetrate, so these are some certain properties which were concluded by Sir Thompson after carrying out the experiment of the cathode rays. So here you can check it out how it looks like, the greenish yellow fluorescence on the soda screen, and you can also check it out the object which is creating a shadow. So cathode ray tube, or rather cathode rays are produced from one end, and definitely it's creating a shadow of the object placed in between its travel. So and on the screen at the background you can check it out. It's producing this greenish yellow fluorescence on the soda glass screen, and they produce a shadow. So these two things we can check it out from here, from the picture. It's a very clear indication and identification. It's also possible that by which both the properties are very clean and clear. All right. So these actually made Thomson to think, since it's the cathode rays are getting deviated and getting rather towards the positive plate and away from the negative plate, Thomson was forced to think that definitely it's containing some particles which are by which they are getting attracted towards the positive plate, and they're not getting deflected or being forced to turn towards towards the positive plate and away from the negative plate. So these conclusions led to the discovery of electrons. And thus the property of electrons are as follows. The first, electrons from all sources are alike, having identical masses. So that means electric, wherever the source. So it was the conclusion that wherever the substance are, if it's an electron, then definitely electrons are having having identical masses, and they look like same. So whatever the problem, when it's an electron, so whatever the source is doesn't matter. So whether it's a normal plastic source, or whether it's non-metal, or whether it's a metal or any other substance, whatever the source of the electron is doesn't matter. So if it is an electron, then definitely it will always be alike in terms of physical properties, alike in terms of chemical properties, and definitely having identical masses. So in terms of reactivity, all the electrons from whatever the substance are will be identical. No difference on those points. Coming to the next we are having they are negatively charged particles having a charge of minus 1.6 10 to the minus 19 coulomb. This is charge of one electron, and normally this is an actual charge of one electron, but normally for during calculation purpose it's the convention. to consider the charge of electron as -1 normally, as a convention, as I said, it's a convention, but the actual charge is -1.6 10 to the -19 coulomb. They are extremely small, radius 10 to the -15 meters, that means in the order of picometers. Okay, so they are extremely small. They're extremely small, radius on the order of 10 to the -15 meters. Probably it's a picometer, only 10 to the -15 meters. So they're extremely small, the size of electrons. The next, we're having the mass of an electron is 1 by 1837 times the mass of hydrogen atom. Mass of an electron is it's 1 by 18, almost 1837 times the mass of hydrogen atom, and that is turns out to be 9.1 to 10 to the power -31 kgs. So to 9.1 multiplied by 10 to the -31 kgs. So this is the mass of an hydrogen, the mass of an electron. Now probably the next property which we're having regarding to that of the electrons, the particles gets attracted towards the positive plate of the electric field. So as it's mentioned that electrons are negatively charged, so it's obvious that particles will get attracted towards the positive plate. So that's quite normal. Alright? Okay. So now here with the discovery of the electrons, with the properties of the electrons, here posed the questions that automatically it came to the mind that if electrons are present in an atom, and atoms are electrically neutral, and atom electrons are negatively charged, then definitely within an atom there are particles present which are just of the opposite charge and opposite characteristics to that of the electrons. And this concept and this idea led to the development of the experiment and followed by with the discovery of the protons. Existence of the positively charged particles was also identified, as I said, and this identification was made by whom? It was made by Goldstein, and first it was with Goldstein and later it was Sir Rutherford. And the experiment, what they did is was an experimental setup similar to that of the what Thompson did, and a similar experimental setup, but they observed that cathode rays. From the cathode rays, if the cathode is placed at the center and the electrical charges are passed, then there occurs another problem. There occurs another thing, that is the charge of a series or radiation, or not radiations rather, charged rays emits on both the sides. One side gets attracted towards, towards the anode, and it's getting deflected towards the positive plate, but towards another side it is not getting deflected towards the positive plate, it's getting deflected towards the negative plate. So rays, certain rays are getting emitted which travels opposite to that of the cathode rays, and those rays which travels opposite to the opposite direction to that of the cathode rays, and those rays are termed as anode rays or canal rays. Anode rays or canal rays. And with the discovery of the anode rays or canal rays, when they were exposed to that of the electric field, definitely they showed deflection towards the negative plate instead of the positive plate. This led to the conclusion that anode rays contain particles which are having different behavior as that of the cathode rays. So what are the properties of the anode rays? Anode rays, they travel in straight line as similar to that of the cathode rays. They're positively charged particles. That's what there goes the dissimilarity. There goes the dissimilarity that anode rays are positively charged, but where it was for the cathode rays, it was negatively charged. So this was one of the major difference between cathode rays and the anode rays, so the canal rays itself. They show deflection in presence of electric and magnetic field in a direction opposite to that of the cathode rays. As I said earlier, that cathode rays got deflected towards the positive plate of the positive plate of an electric field, whereas anode rays go deflected towards the negative plate of the electric field. They penetrate through matter, as common with that of the cathode rays. They penetrate through matter, and they produce fluorescence on zinc sulfide screen. So now the cathode rays used to produce fluorescence on, if you remember, soda glass screen. Cathode rays used to produce fluorescence on soda glass screen, whereas anode rays produce fluorescence on the zinc sulfide screen. So these were some of the difference between the experiments done, experiments of the cathode rays, or rather conducted with cathode rays, or not conducted with cathode rays rather, where cathode rays produce fluorescence on soda glass screen was done by Thompson. Then Rutherford, they observed that anode rays used to produce fluorescence on zinc sulfide screen because they use zinc sulfide, and they traveled opposite in the direction to that of the cathode rays, and used to produce and used to get deflected towards the negative negative plate, whereas cathode rays deflected towards the positive plate. So with that, with those properties coming to led to the discovery of the protons, and the properties of the protons lies as properties that are having protons are having the same mass as that of the hydrogen atom. Protons are having the same mass as that of the hydrogen atom. The next they're having unit positive charge plus 1.6 10 to the power minus 19 coulomb. If you remember, electrons were having minus 1.6. The charge that they are having the equal charges. So positive, as I said, that since atoms are neutral in nature, so electron, the total charge of the electrons has to be the same as that of the electrons, because there are particles present. So the electrons are now protons are having exactly the same charge, but of the opposite nature that of the electrons. So it's plus 1.6 10 to the power minus 19 coulomb. The next we are having, they're extremely small in size, more or less a similar sort of particle size. Electrons also was of the order of 10 to the minus 15 meters. Protons are also having the similar sizes, 10 to the minus 15 meters. The next we're having is 1837 times the mass of an electron that resides in the central part of an atom. That means protons are much heavier than electrons. So protons are 1837 times the mass of an electron. So protons are almost 187 times the mass of an electron. That much heavier. So electrons are the lightest particles present within an atom. Electrons are the lightest particles present within an atom. And whereas in 1837, as you can check it out, with 1837, it's basically almost nearly 2,000 times heavier than the mass of an electron. And protons are present in the central part of an atom. Protons are deflected towards the cathode plate in an electric field. Protons are deflected towards the cathode plate in an electric field. Cathode plate in an electric field. So cathode plates are basically negative charge plates. Now, followed by these properties, there is a question which arises, that is, how the electrons are arranged inside an atom. The question, as I said, arises with these sort of properties coming into existence or into the limelight. The question arises that how the electrons are arranged inside an atom. That means the structure of an atom, how an atom looks from inside. Now, with this question to be answered, J.J. Thompson, he put forward a model. He proposed a model which called a plum pudding model. He said that the electrons and protons, both the charged particles which are present inside an atom, they are present as if plums are present inside the pudding. We all know how the pudding is, and the way the plums are, or the dry fruits, all those things are distributed within a particular within a pudding. In a similar way, the charged particles, the positive and the negative charged particles, are scattered and distributed within the atom itself. The only criteria is with every negative charged particle, something like this. With every negative charge particle, a positive charge is associated. So with the negative charges are scattered, the positive charges are also scattered. The only thing, all the scattering is happening in pairs. Pairs means that the positive charge is accompanied by negative charge, or a negative charge is accompanied by a positive charge. So this was Thomson's concept, as he said, that how the way lumps are distributed, when are scattered within a pudding, exactly in a similar way, electrons and the protons, they are distributed within an atom in a similar way. But there lies a problem. Later on, it was rejected. Later on, it was rejected. Rejected by whom? Rejected by Rutherford. Rutherford rejected this model, that is this plum pudding model. Rutherford rejected this plum pudding model. Definitely, Thompson was surprised. Thompson was surprised, and he asked the question, or not only him, the others also, that if Rutherford is rejecting this model, what's the reason? Why he is rejecting this model? This plum pudding model. What was the reason of rejecting this model? Rutherford said, observations did not match. His experiments are revealing something else. So whatever the experiments which he is conducting, those experiments, the experimental results are not matching what plum pudding model is expressing. What Thompson is proposing through plum pudding model is not at all correct. Whatever the experiments, the experimental results, what he is having with him. The observations, what he is having with him. Observations. Everybody was surprised. Observations did not match. Interesting. Then, the questions will come. Please, what are the observations? The observations now, Rutherford said, that to know the observations, or rather, it's also, in order to know the observations for all of you, you need to know the experiment. In order to know the observations, you need to know the experiment, and that experiment is gold foil experiment. Rutherford's gold foil experiment, if you know, then definitely after going through the experiment, you will also feel that plum pudding model is not correct, is not valid. Now, let us move on. Gold foil experiment. The experiment arrangement was something like this. There was a lead block. Lead is basically an element or a metal which absorbs many sorts of radiations, and there is a radioactive source. That means a substance which is highly reactive in nature, and if it is kept open, this element, it emits radiations. So that particular substance has been placed inside the lead block, and there was a slit, a small opening inside the lead block. Definitely, when it's emitting radiation, the radiations will come out through that slit or the opening, as you can see over there. As you can see over there in the picture, there is the red line is coming. It's all coming out from the lead block, that particular source, its opening, and it's entering. There is it's going to hit a screen. There is a fluorescent screen being placed in between, in the path of the radiations which are coming out from the lead block. Those radiations are traveling and hitting on the screen, but there is another barrier. In between, before the screen, it has to pass through a gold foil. It has to pass through a foil made of foil, and that foil is basically none other than a gold foil. It's basically elemental gold, rather that gold element is made thinner, and the thickness is almost about 0.0004. 4 zeros, and after that 4 centimeters. So this thin, it's a very thin foil. It's been placed in the path through the path in between which the radiations are traveling, and it's hitting the screen. So before it travels and before it hits the screen, it has to pass through the gold foil. What are the observations now? This was basically for bombarded gold foil with 0.00404 centimeters thick with alpha particles. Alpha particles, what are alpha particles? They are charged helium particles actually. Their alpha particles are positively charged helium particles, is represented like this way, 4He2 whole thing to the power plus. So if you remember, helium is basically having atomic number 2, so that means 2 electrons, 2 protons, and 2 neutrons. So 2 positive means it's having 2 protons with no electrons present. So the shells, or so whatever, all the electrons within the helium particle, these alpha particles, are not existing. So the electrons are not present within the alpha particles. These sort of particles, the highly charged particles, are coming out from their source and is hitting this gold screen, gold foil, and then after hitting them, passing through and penetrating through and traveling and then striking the fluorescent screen. What are the observations? Now, based on this, Rutherford concluded. Rutherford made an observational list. The first, he concluded that most of the space inside an atom is empty because most of the alpha particles pass through the gold foil without getting deflected. That's for the first one. So they're passing through and hitting in a straight line wherever it should have been hit. Where it should have hit, it's hitting the same point. So that means most of the space inside an atom is empty. So alpha particles didn't get any deflection. The second, very few particles were deflected from their path, indicating the positive charge of the atom occupies very little space. That means very few particles of their were deflected. That means alpha particles are traveling only very few. Rather, on this, there are very few on the fluorescence being noticed on some other sections of the screen. So such less fluorescence reflected that very few particles got deflected, indicating positive charge at the center of the atom. There are positively charged center in an atom called nucleus. Nearly all the mass of the atom resides in the nucleus. It means electrons are very lighter. So the difference in the mass, for that reason, atoms are almost 2,000 times heavier, 2,000 times heavier than that of the protons. So that of the protons, and hence positively charged nucleus is carrying the entire masses. The size of the nucleus is very small as compared to that of the atom. That's obvious. That we know that because the electrons are of 10 to the minus 15 meters, definitely the nucleus is also has to be very small. The electrons revolve around the nucleus in well-defined orbits. So Rutherford proposed that electrons are revolving around the nucleus. They are not stationary, they are revolving around the nucleus and in specific designated paths. They are not scattered like the Plum-Pudding model. Okay. Now this led to Rutherford to propose his, and of course atoms are electrically neutral, to propose his atomic model. And in 1911 he proposed his atomic model, and it looks like this, with the central part is having the nucleus followed by surrounded by orbits, and our orbits are basically paths where electrons are rotating around the nucleus. And those paths are fixed. Electrons do not change their paths, so they're constantly rotating around the nucleus in their fixed paths. So considering based on this Rutherford's model in 1932, later on, James Chadwick also proposed that there are not only the rather electrons and protons, there are another particle which existed inside nucleus, and because James Chadwick, that's the person who compared the total mass of the protons and as well as the electrons, the cumulative mass do not match with the mass of an atom. The cumulative mass of electrons and protons do not match with the mass of an atom. So definitely Chadwick became inquisitive that there are some other particles which are also present inside the nucleus, inside an atom, which are existing, but due to which the masses are not matching. So with that intuitiveness, James Chadwick, he discovered the existence of neutrons, because since electrons and protons are positively charged, those particles has to be neutral, but with a probably higher mass. They are having high mass but no charge. They are neutral particles, and thus led to the discovery of neutrons. So the discovery of neutrons, definitely there are neutrons having properties. The first, neutrons are the heaviest particle in an atom. It's slightly heavier. It's comparable. Its neutron's mass is comparable to that of the protons, but definitely it's the heaviest particle in an atom. They're having no charge, like neutral particles. They're extremely small in size, at the order of 10 to the minus 15 meters. Mass of a neutron is 1.67, 16 to the power minus 24 kg. That's 1 AMU. And they remain unaffected in an electric and magnetic field. These are some of the properties of neutrons. And 1 AMU is atomic mass unit. Atomic mass unit. These units will be required in the higher classes for when we will proceed with certain calculations. Calculations of atomic masses or mass of an atom is expressed, mass of an atom is expressed in terms of AMU, atomic mass unit. So that's all for the discussions and the lectures and about the experiments of the history, how these particles are discovered, how the experiments were carried out, what are the experimental setups were there. So these were the historical points and what those people have done to bring out or to bring forth the hidden mysteries from a particular substance and within the nature. So that's all for today's this lecture. I hope you will like it and enjoy it. Till then, stay at home and take a very good care of yourself. Thank you so much.